Hello everyone. In this lecture we are going to look at analytical solutions to our governing differential equation, specifically 2D profile modeling. Now for really complex problems we often use a numerical solution like finite difference or finite element models. We've seen flow net solutions, but if you have simple enough geometry, you can directly derive an equation to the governing differential equation, a function which satisfies that, and apply it to simple conditions. So that's what we're going to do. We're going to be focusing on 2D profile models, and that is basically a vertical slice through a dam or a levee or a problem. Well, a sheet pile might be too difficult to use with an analytical solution, but we are going to handle a couple of simple solutions. We will look at two examples in particular. One will be a flow through a rectangular section, and the other will be seepage through an earth dam. And we can come up with equations to describe both of these. And for the rectangular section, we're going to look at a couple of different solutions. Now, before we derive our solutions for both the rectangular section and the earth dam, the trapezoidal earth dam, we are going to derive a special version of the governing equation that applies to these cases, and we'll use that to come up with these other solutions. And in order to come up with this governing equation that applies to profile models, we are going to apply what are called the dupuit assumptions. I believe that's a French name, dupuit it's pronounced. And there are three dupuit assumptions that we need to be familiar with. Number one, the exit point coincides with the tailwater. So on the back end where the phreatic surface exits the saturated region, that coincides with the tailwater on the back end. In reality, it coincides above that. We have a graphic of that in a minute. Number two, the hydraulic gradient is constant along a vertical line. And three, the hydraulic gradient is equal to the slope of the free surface. So this is what I was talking about with assumption number one. The bottom represents the actual exit point. So this is a dam or a levee, and we have the free surface through the dam or levee, and then this is our tailwater, and it actually exits somewhere back here, and then the water runs down the back. We are going to assume it exits right at that tailwater, and that it's fairly close to reality, but it is a simplifying assumption. Number two, the hydraulic gradient is is constant along a vertical line. So another way to express this is a hydraulic gradient, dH dx, is independent of y. And this is a good assumption if the flow is primarily horizontal. So if you pick a vertical line, the hydraulic gradient is constant along that vertical line. And then finally, number three, the hydraulic gradient is equal to the slope of the free surface. So if this is our free surface, their phreatic surface, the slope of that line would be delta H over x, which is the tangent of x. In reality, the hydraulic gradient is the change in head divided by the length of flow. And along that free surface, the water is flowing parallel to the free surface. So this is the actual length of flow. So basically, we're going to use the tangent of alpha instead of sine of alpha is one way to look at that. Now, what kind of assumption is this? This chart shows for a range of alphas, slope angles of the free surface. Again, so the sine would be the actual, and the tan would be the simplifying assumption you get with the dupuit assumption number three. And as you can see, up to about 20 degrees, there's very little difference. And once you get to 30 degrees or beyond, there's a difference between the two. Now, it is extremely rare that we would have a phreatic surface sharper than 20 degrees in slope. Could happen in very low permeability materials. So it's possible, but this is not a bad assumption. Okay? All right, so these dupuit, we're going to go back to the governing equation and apply the dupuit assumptions to come up with a new form of the governing equations. So, since the hydraulic gradient is constant along a vertical line, the dH, another way to express this is dH dy equals 0, so the head does not change along a vertical line. And so the flow in the y direction is 0. So we're assuming that the flow is one of the main byproducts of the dupuit assumptions is we're assuming horizontal flow. When in reality, as you're flowing through an earth dam or a rectangular section, there's going to be a vertical component, but we're just assuming it's horizontal flow. All right, now when we derived our governing equations, we used a representative 3D element. And in this case, we are going to use this representative slice, which is of width dx. The line of seepage is a phreatic surface at the top. The height of that measured to relative to the bottom, that's going to be our our head. And so the shape of our element here is dx in width, h high, and then it's a 1 foot or 1 meter in the opposite direction, so a unit. The other direction is just a single unit. And then we're going to look at flow in the x direction through this element as we go through this derivation. So we're going to assume that the hydraulic gradient is equal to del H del X, which is, again, the slope of this free surface up at the top. The flow is horizontal, so the direction of flow is dx. H is a saturated thickness. And again, we're going to do conservation of mass, the continuity equation. So we're going to say the flow out the right side of this element is what flowed in the left side plus del Q del X dx. That's basically the amount that the flow rate changed as you go from the left to the right side of that element. And then for conservation of mass, Qn minus Q out has to be equal to 0. So since this is Q out, we substitute that right here in this equation. And these Qn minus Qn's cancel. And we get minus del Q del X dx equals 0. We can divide by negative dx, and we get simply the derivative of Q with respect to x equals 0. All right, and for Q, we can just plug in Darcy's law, which is KIA. And K is the hydraulic conductivity. The hydraulic gradient, as we've mentioned before, is del H del X. The cross-sectional area of flow is the height of that element times its dimension in perpendicular to the screen, which is 1. And so we pull the H as a constant, we'll pull to the other side, and we get this expression, the derivative of KH del H del X equals 0. And if you take the second derivative of H squared, you get 2H del H del X, and therefore H times del H del X is equal to 1/2 the second derivative of H squared. And so that is significant because this H del X is this term we have right here. So if we plug that in, we get this expression, and we can pull, since K and 1/2 are constants, we can pull them out. And again, we can divide by 1/2 K since we have a 0 on the other side. And now we're left with del squared h squared del x squared equals 0. So the second derivative of h squared is equal to 0. This is kind of similar to the Laplace equation we had before, which was the second derivative of head with respect to x plus the second derivative of head with respect to y equals 0. But there's no flow in the y direction, so we get rid of that. And then the other difference, when you apply the dupuit assumptions, the main change in your governing equation, well, the y term goes to 0, but we have, instead of the second derivative with respect to h, we have the second derivative with respect to h squared. So whenever you see that h squared in a governing equation, you can, a little bell should go off in your head, and that means the dupuit assumptions were assigned. And again, this is called the Dupuit-Forchheimer equation, and this is what we will use to solve for the analytical solutions for our special cases.